Section 3.8 Related Rates. The problem of finding a rate of change from other known rates of change is called a related rates problem. What I'll do is give you an example before we can show you the procedures of, then I'll show you the procedures of finding or solving a related rates problem. Example 1. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right, so picture a balloon and air is being pumped into it. So let's just look at one sphere in general, and it's got, of course, a radius and a diameter. And now we are asked to find how fast is the radius increasing while we are pumping air into the balloon at a particular point or time when this diameter is 50 centimeters. This is a related rates problem because we were given a rate of increase, or a dV by dt, of the volume of the balloon. So if we let V be the volume of the balloon, or the sphere in particular, it's equal to 4/3 pi r cubed. And it says here that the volume increases at a rate. So that tells us that dV by dt is equal to 100 cubic centimeters per second. And it says we are to find the rate at which the radius is increasing. So we are to find dr by dt. We begin with the equation of the volume that relates with the radius of the sphere, and it's 4/3 pi r cubed. And what we're going to do right now is to differentiate both sides with respect to, so we differentiate both sides, and I will use this shortcut, with respect to the variable t, as in time t. So if I differentiate both sides with respect to t, that means the volume changes with time, the radius changes with time, so each of these variables are functions of time. So I'll go dV by dt will be equal to 4/3 pi times the derivative of r cubed, which is 3r squared, times, because this is just taking the derivative with respect to r, now we have to multiply by chain rule the derivative of r with respect to time. And it says we are to find dr by dt. So if we simplify a few things here, and if I solve for dr by dt, we will get dr by dt means we multiply both sides by the reciprocal of the coefficient of dr by dt and multiply it to dv by dt, and that's equal to, well, let's go ahead and put dv by dt here. So multiply by the reciprocal of all this is 1/4 pi r squared. And now that we have differentiated and solved for dr by dt, we can now substitute all that is given. So dV by dt is equal to 100 cubic centimeters per second multiplied by 1/4 pi times the square of the radius at the moment when the diameter is 50 centimeters, which means this is 25 squared. And all that will just give us, that cancels out the 4 into here, so 4 goes into 125 times, which means we cancel out one of the 25, so we are left with 1/25 pi. And the unit of measure is, there's a cubic centimeters on top, and you divide it by a square of the centimeter, gives us centimeter per second. So this is now the rate of increase of the radius at the instant where the diameter was 50 centimeters. Related rates problem strategy. Number 1. Draw a picture and name the variables and constants. We did that with the sphere. Okay, use t for time and assume, of course, that all the variables are functions of time and that they can be differentiated. You can take the derivative of all the variables. Write down the numerical information, in other words, all that's given, write it down. And then also write down what you're asked for. Usually it's a rate. So in our problem, we were asked to look for dr by dt. And then write an equation that relates the variables. So what we wrote was the volume equation that relates the radius. So 4/3 pi r cubed. And then after we write the equation, we differentiate it with respect to time, and we did that. And then we got an expression in terms of dv by dt and dr by dt. And then we solve for dr by dt and we evaluate, the last one is we evaluate all the information that's already given. That's the only time we plug in to find the unknown. Okay. Some of the things that I said a while ago was that we substituted the given after we differentiated. Okay, so when the given information is a rate of change and when it is at an instant, the only time we substitute those numbers is after we differentiate. Of course, it's different if you have just a fixed value of a variable or a fixed value of a height, fixed value of a radius, etc. Okay. The given information and the unknown will hint on what equation to use. For example, in example 1, dv by dt was given, which means I would be looking for the equation of the volume, and then the unknown was dr by dt. So this is given, and the unknown was dr by dt. So the natural thing to do would be to relate volume and radius of the sphere, and that's what exactly we did. So the given information and the unknown will hint on what equation to use. And then I was looking at, remember when we solved for dr by dt, this should be in terms of centimeters per second, and sure enough, we were consistent with our unit of measure. And there would be cases where we need to convert, and depending on what the problem is asking for. So we need to convert the rate of change as well, just in terms of the unit of measure. All right, so how about we go ahead and solve problems. Example 2. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder, okay, there's the bottom of the ladder, slides away from the wall at a rate of 1 foot per second, okay, it's moving away at 1 foot per second, how fast is the top of the ladder sliding down on the wall, when the bottom of the ladder is 6 feet away from the wall? And what I did here is I drew a right triangle which the ladder created with the ground and of course the wall. And we can now we can now analyze a right triangle right there. So this is now the ladder, and the ladder is a fixed length, so we can go ahead and write 10 here. Now the distance from this point to this point would be the distance of the end of the bottom of the ladder from the wall, so let's call that x, and then the distance from the ground to the top of the ladder would be y. Now it says here that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So that means it's a rate, so we write this as one of the given, dx by dt is equal to 1 foot per second. And it says how fast is the top of the ladder sliding down the wall. So that means we are to find dy by dt. Now, dy by dt is an instantaneous rate of change, so it's how fast is the top of the ladder sliding down when x is 6 feet. So find dy by dt when x is equal to 6. Okay. Now, based on the picture, what would be our equation that would relate all these three information and three variable? What would be the equation that would relate x, y, and 10? Of course, it will be the Pythagorean theorem. So let's go ahead and write the Pythagorean theorem. So our equation would be x squared plus y squared is equal to 10 squared. This is now the equation that relates the variables. The next thing we need to do is to differentiate both sides with respect to time. Differentiate x squared, we get 2x, and we don't stop there because x is a function of time, so times dx by dt plus 2y, the derivative y squared, multiplied by the derivative of y with respect to time, and of course the derivative of a constant is 0. Now we are to solve for dy by dt, which means, well, first of all, let me go ahead and cancel 2 on both sides, and we'll have dy by dt. Put this term on the other side will give us the negative of x dx by dt, and of course the coefficient of dy by dt is y, so we divide everything by y, and that's how we get the y there. Now, are we ready to substitute the given? Yes, because we've already differentiated. Now it says when x is 6, we can plug the 6 there, we can plug in the value for dx by dt, but what is y? So to find y, we substitute it, or rather we solve for y using the Pythagorean theorem when x is 6. So this is 10 squared minus x squared is 6 squared, and that's just equal to 100 minus 36, 64. Take the square root of 64. That gives us 8. So this is equal to negative 6 over 8 times 1 centimeters per, or rather foot per second. So if we simplify, that gives us the negative 3 over 4 foot per second. So the rate at which the top of the ladder is sliding down is 3/4 of a foot per second at the instant when x is equal to 6. Okay. First problem, or rather example 2, solved.